Hi everyone, my name is Ramya Krishnamurthy and I have got Ajay Kumar with me. I have an overall industry experience of 17 years in the storage domain, and Ajay Kumar also has almost 13 years of industry experience in the server and storage domain. Both of us work at HPE in the storage division, working on different HPE storage solutions with 3PAR and Primera. We will spend the next 40 minutes or so to talk about the off-chain storage for blockchain. Well, it does sound like a lot of jargons. So let's look at the agenda and delve deeper into the session. So what are we going to cover? We will talk about an overview of blockchain and the fundamentals of off-chain storage, where it is used, what are the use cases, performance and scalability aspects related to off-chain storage, how we can achieve them, how to provide low total cost of ownership for off-chain storage with data reduction technologies such deduplication, protecting off-chain storage data with backup and disaster recovery. And in the end, we will spend some time on a vendor-specific example with off-chain storage requirements. So with that, let's go ahead. So let's start with blockchain quick overview. So what is a blockchain? In a simple term, like the name indicates, blockchain is a collection of records that are linked to each other. So blockchain is a distributed database of records stored in blocks. The data stored in blockchain cannot be modified or deleted and remains immutable. The records stored on a blockchain can include information about people, transactions, contracts, or practically anything that can be described as data. So in a blockchain, what does each block contain? Well, each block contains data, hash for the block, and hash for the previous block. In any blockchain protocol, the first block is called the Genesis block, and the subsequent blocks are added to it to form a chain of blocks. After the block has been added to the end of the blockchain, it is very difficult to go back and alter the contents of the block. That is because each block contains its own hash along with the hash of the block before it. Hence, the data within the blockchain becomes immutable. The various blockchain platforms like Bitcoin, Ethereum, Hyperledger, Corda, each have their unique schemes of verifying and recording transactions and adding data onto the blockchain. These schemes help to ensure the security and immutability of every entry. Now, the blockchain can be a public or a private blockchain. Examples for public blockchains are Bitcoin and Ethereum. Examples for private blockchain are Hyperledger and R3 Corda. So what exactly is a public and a private blockchain? In a public blockchain, everyone can participate as the members of the community, and all the transactions carried out on the public blockchain are open, and everyone may inspect the details of the transaction. Whereas in private blockchain, it differs. This is also called as a permission blockchain, where the participants needs permission to become the part of the network, and the transactions are private and open only to the participants that have been granted permission to access the network. Major use cases of blockchain are in the sector of financial service, healthcare, and supply chain. In healthcare, providers can use blockchain to store medical records of their patient. It can be written onto the blockchain when a medical record is created and the records cannot be altered. In a supply chain, the suppliers may use blockchain to record the origin of the products they brought. This would allow the marketers to check that the goods are authentic. Now, talking about storage infrastructure for blockchain. Blockchain storage needs massive scale and performance, resulting from petabytes of records and distributed access. Proposed talk, however, here is not to talk about how the blockchain works. We intend to cover the aspects of the storage infrastructure needed for blockchain, which is a critical element in the blockchain environment. So now coming on to off-chain storage. In simple words, transactions which are executed within a blockchain are called on-chain, while the transactions which are executed off the blockchain or outside the blockchain are referred to as off-chain. We can manage or store the data for a blockchain-based solution either as an on-chain or an off-chain storage mechanism. However, storing all the blockchain data using an on-chain mechanism is not cost efficient, and such large amount of data can bring in scalability challenges as well. A large significant amount of information in the implementation of blockchain is unstructured data in the form of files, contracts, records, emails, or even images. These wide unstructured data did not reside in the blockchain and require a different storage mechanism, which is what we refer to as off-chain storage. So with off-chain storage, we store only the hash of the data in the blockchain and store these large data sets such as images or large document files on an off-chain storage. Another common use case for off-chain storage is to store sensitive private data which do not have to reside on the public on-chain. As the name suggests, an off-chain storage solution offloads the heavy lifting of large data sets from the blockchain nodes. This off-chain data must be shareable and accessible, and hence, even if this data exists outside the blockchain, an immediate access to this shared data is always a requirement, and every blockchain implementation must have a high performance, a high scalable, and easily accessible off-chain storage. So, what's needed to provide this efficient off-chain storage? Well, few attributes are a desired performance, a scalable storage, and then we should have data protection in place. So let's talk about these off-chain storage attributes in our next few slides, starting with NVMe flash technology. Now, off-chain storage reduces the burden of storing large data sets off the chain, but it has an effect on performance since the physical disks are slow. NVMe technology can help to minimize the storage processor cycles and provide the necessary performance on a scale since it bypasses the slow SATA bus and communicates directly with the CPU, providing a greater bandwidth, IOPS, and low latency to increase the performance of an off-chain workload. As you can see in the diagram below, how Flash has evolved. Flash was initially based off SAS and SATA drives, and then it evolved to NVMe based drives, and then we have NVMe with storage class memory. Storage class memory technology into the storage infrastructure, along with NVMe backend storage disks, can provide much more significantly improved performance for random read and write workloads. So imagine it's like this. If a storage controller that sits between the server and the backend flash drives and cannot keep up with the flash drive speed, they actually become the bottleneck in the speed. Hence, an overall solution requires NVMe flash drives at the backend along with NVMe storage class memory, which closes the gap between the memory and the storage and strikes a balance between performance, capacity, and cost. So what exactly is the storage class memory? The storage class memory is a type of a NAND flash, and because of its DRAM-like capabilities, it is often referred to as persistent memory, which ensures persistent data even when there is a power failure. Hence, as I said before, the main advantage of storage class memory includes less latency and increased throughput in comparison to just flash SSDs. NVMe technology, along with the storage class memory, helps in improving the overall off-chain workload performance. So if we look at one of the blockchain use case of financial sector, NVMe with storage class memory enables rapid processing and execution of financial transactions. Now we have Ajay to talk about the next few aspects like scalability and data reduction. So over to you, Ajay.
Thank you. Uh, so we'll go with the scalability portion of the section here. Few transactions in blockchain can easily lead to the generation of document in an unstructured form. So you can see the requirement of blockchain increases significantly with the increase in the number of transactions. As the number of transactions per second increasing over the time, the storage requirement of blockchain also increases significantly. So as expected, we can see if the transaction produces a one document for every 3 or 5 transactions recorded, this is based on the industry standard, the off-chain storage requirement for a blockchain will soon exceed by an order of magnitude. Likewise, performance also needs to be scaled up with an increase in the unstructured data. The storage capacity is a storage device most important requirement. The second most important storage criteria is what happens when you need an additional space. Your choices can be as simple as installing a new drive cell or as complicated as constructing a new data center. Scale-up architecture, however, is limited to the storage controller scalability limits. If the storage controllers have hit their performance or power limits, then the only choice is to install a new device as you transfer storage and handle the load between the two controllers. This becomes highly complex to manage. Inefficient distribution of resources becomes a challenge when it comes to determining where the workload needs to live. Hence, the storage needs to be scale-out capable. Scale-out includes adding the new nodes into the cluster and redistributing the data across these nodes. It adds additional disk storage and performance, capacity, as well as additional RAM, CPU, and networking resources to increase the overall performance of the cluster. We can serve the storage requirement with either by scale up or by adding scale up by adding disk and disk enclosures or by just adding the nodes. That is what we call it the scale out. without disruption to the availability and accessibility of the blockchain, which is required very much. Yeah. Coming to the slide of the data reduction, we'll see here why in a off-chain storage we need to have the storage arrays which with a data reduction capability. Data is getting generated at a rate that exceeds the growth in the storage capacity. Thus, data storage is becoming increasingly challenging. With the growing uses of SSD media, deduplication has become important for the primary storage arrays. In addition, since the primary storage shift towards the SSDs, solid state drives, which have higher per byte cost compared to the hard disk drive. Price consistency is a very critical factor here. Using deduplication and compression technologies, we can achieve a spatial savings. This will allow us to use the complete capacity of the system. Also, total cost of ownerships can be reduced with deduplication and compression technologies. Deduplication and compression can be combined to help maximize space savings. In an all-flash storage arrays, inline deduplication reduces the overall need for the capacity. Depending on the application, the data reduction ratio of 1:4 can be easily achievable. Even with the example we have, which we'll go through in the last slide, we have this particular ratio to be at about the 1:4. So the data reduction ratio is amount of storage space saved by the combination of both deduplication and compression. With deduplication enabled, 15-16 TB of a storage space can perform at the same level as a 50 to 70 terabyte of a data array. You can see how these levels the capacity playing field between the all flash and the traditional storage arrays. This will also help if multiple copies of the same data are stored within the same node as is the requirement in the blockchain, particularly the off-chain storage of the blockchain. The blockchain data will have a lot of duplicate data. As for each transactions, if we are modifying the off-chain data structured format, which we talked in the previous slide, which is these are already stored in your storage arrays. And with every transactions, whenever we are modifying these data, we are creating a new copy into the same storage arrays. So this data duplicity problem can be solved by using the array with the data reduction capability. To visualize this, we have plotted the graph. So let's simplify the off-chain storage by seeing this on the graph, which will give us much more visibility. In the graph, we can see the difference in the storage uses in comparison to the data reduction enabled storage arrays versus simple storage arrays. You can see here in the yellow line. So the right hand axis talks about the 110, 100,000. This is the number of transactions per second. And on the left hand axis, it talks about the how much storage you are seeing the increases of the users in terms of a TB. So you can see here the yellow line indicates the amount of storage off-chain is going to consumed based on the number of transactions per second. So you can see once it crosses the 1,000, it increases very drastically. So the the amount of storage required will be somewhere in the range of 20,000 TB. Now coming to the same data with the data reduction capable enabled array with the inline deduplication and compression, we can see the purple line going here, which is drastically reduced. Even if we go to the number of transactions per second to a 30,000. So the same storage can be drastically reduced which you are seeing here in the purple line. So the data reduction plays a very efficient role or very important role in the off-chain storage. Yeah. Over to you, Ramya.
Thank you, Ajay. Now, moving on to the next aspects, one being the data protection. So, let's look at why data protection is important for off-chain storage and the means to achieve the data protection. The table stacks for off-chain data are stable backup and recoverability, and off-chain storage requires data backup mechanism. Off-chain data backups can be done by using point-in-time copy. The ability to create the point-in-time copy of data when an application is online is essential to the development of backups. So, what are these point-in-time copies? A point-in-time copy is a snapshot of the original data as it existed. These point-in-time copies are immediately generated in seconds, and users can make hundreds of these copies at no extra cost. Users also have the option to either have a read-only copy to prevent any changes or a read-write copy to enable modification or restoration of snapshots. Like any other backup, an ability to recover, restore quickly to the previous point-in-time copy is critical for off-chain storage as well. But the important point to note here is these point-in-time operations should not adversely affect the performance of the blockchain storage and should only consume a limited additional space. We can as well set the data backup retention policies based on the retention time and the archival rules for the off-chain storage. For instance, a daily incremental and a weekly full backup of an off-chain data can be performed to the required retention period. So as you see in the diagram, we can have multiple copies of an off-chain storage, which can be either a read-write or a read-only point-in-time copies. And we can use this point-in-time copies to back up these data onto a backup device. And based on the retention policies, we can perform these backups on the off-chain data. Now, moving on to the next aspect, which is replication. Now, coming to continuous data synchronization or replication. An off-chain data must be replicated to a different storage system at the same site or a remote location for different reasons. Like it could be for disaster recovery, backup, or a data transfer. The ability to replicate the data in the most efficient and cost-effective manner to the remote location is a must for off-chain data. This can be achieved by replication solution, either asynchronous or asynchronous replication. Choice of the replication technology depends on the recovery point objective, which is RPO, and the recovery time objective, which is RTO, which can be aggressive for off-chain storage. When we talk about RPO and RTO, RPO is the maximum amount of time that can be lost in an event of disaster, and RTO defines the maximum amount of time that elapses following a disaster before the application is back online. So as we can see in this diagram below, synchronous replication has zero data loss and zero RPO. That's because synchronous replication writes data to the primary storage and to the secondary simultaneously. That way, the primary copy and the replica always remain synchronized and there is zero data loss. But this whole process adds latency to the host writes. Whereas in asynchronous replication, we can see a minimum amount of RPO. That's because here the data is written to the primary storage first, and then it copies the data to the secondary. So there is a delay before the data is copied to the secondary site. But since the host write is acknowledged as soon as the host writes are completed on the primary, the latency to the host writes is minimal. Asynchronous replication is suitable for environments that needs to replicate data where a higher RPO can be accepted, but we cannot afford long write IO service time. In HPE storage, which is our proposed storage for offchain storage, we support all the above replication technologies along with the disaster recovery solution called remote copy synchronous long distance topology SLD, which allows data to be replicated from one storage to two different storage arrays by replicating the data synchronously from primary to secondary, and at the same time replicating the same data via asynchronous mode between the primary and the third storage array. So as you see, there is a lot of data redundancy. All the above storage technologies will help in continuous data synchronization for the off-chain storage. Now, let's talk about the vendor example in detail and our proposed storage for off-chain storage. So, HPE Mission Critical Distributed Ledger Technology, commonly called as MCDLT, is a solution that enables customers to run distributed ledger workloads on the highest availability enterprise platforms. HPE Nonstop, which is the core of HPE MCDLT solution, creates a play for mission-critical nonstop solutions around cloud technology. It offers a very high level of availability and near linear scalability for workloads in modern virtualized and cloud environments. As you see here, the MCDLT solution is based on an HPE virtualized nonstop system, which is deployed in a cloud environment such as Red Hat OpenStack or VMware vCloud to provide the service infrastructure. You can deploy the virtualized non-stop infrastructure as a service system using industry standard servers and networking protocols. The cloud here is built using HPE ProLine servers connected over high-speed fabric. This fabric is built using HPE InfiniBand NIC in the servers connected to the Flex Fabric switch. The solution is built using a CODA Enterprise, a permission distributed ledger platform, and the non-stop virtual machines are deployed over the IaaS to form a complete non-stop system. HPE Storage here will serve as an off-chain storage provider for MCDLT solution. The scale-out nature of the HPE storage is best suited for mission-critical applications, providing the desired performance with the NVMe technologies. So in the next slide, we will see how with HPE storage, we can get the better performance and increased IOPS and less read service time using the NV storage class memory in both read and write intensive workloads. So we have plotted this graph, and as you can see in the graph, the first graph is the throughput for write intensive workload. And as you can see, the IOPS for the NVMe storage class memory with backend NVMe drive is the highest, which is plotted with black color in comparison to the SAS SSDs and the spinning media. Likewise, in the next graph, you can see the read service time for the read intensive workload. And again, we see the latency for NVMe storage class memory with the backend NVMe drives is at the lowest. in comparison to the SAS SSD and spinning media, and the highest being the one without the storage class memory. So with this, we come to the end of our session. It was a delightful experience to present our thoughts on this topic. I and Ajay will be happy to take up any few questions on this topic. Thank you.
Thank you.